Alright guys, so today we are going to be learning about Chapter 3, Section 1, and it's titled Solids, Liquids, and Gases. However, we're actually not going to be learning just about solids, liquids, and gases, but instead we're going to be learning about all 5 states of matter. Okay, so there are 5 states, and so the first 3 naturally are solids, liquids, and gases. The fourth most of you probably have heard before, and I believe I mentioned it in class once before in Chapter 2, but it's something that occurs at extremely hot temperatures, which would be a plasma. And the fifth state of matter is one that you haven't heard of as much before. Some of you might have, but majority of people usually haven't. And it occurs at extremely low temperatures, and that is at or near absolute zero, which is, once again, 0 degrees Kelvin. And so the 5 states of matter, and you're going to want to write this stuff down, 5 states of matter would be solids, liquids, gases, plasmas, and this BEC. And so the BEC stands for Bose-Einstein condensate. So I'll go ahead and add that in here, that it's Bose-Einstein condensate. And you can see then at the bottom of the screen I have in there, so I'll write it in for you guys. So it's spelled Bose. It's based on 2 scientists. Naturally, you guys know the second scientist. And condensate. Okay, and so naturally it's abbreviated BEC, as you can see, and it's real simple to see then. It says that at the bottom, the differences between the states of matter depends on the amount of kinetic energy of the molecules. So what we're going to be doing, and this is going to be really important to kind of jot down too, the key here is this amount of kinetic energy. So we know that kinetic energy is this quantity, and really what it's doing is it's going to be measuring how quickly the objects are moving, or in other words, in this case, it's going to be how quickly the tiny particles of matter are moving. And a lot of these, it's going to be atoms, but in, for example, plasma, we're going to see that it's actually going to be ions that are moving, and it's not just atoms. Okay, so as we're going through the notes here, we're going to go through one by one. There's going to be about 5 things you're going to write down for each. So if you wanted to kind of in your notes list them, you're going to start out with, we'll go in the same exact order, so we'll start out with solids, then go to liquids, gases, plasmas, and then lastly to BEC. And that way you'll be able to have the same kind of notes in your notebooks. And so once again, if we need to pause the video at any time, then you can pause the video. If you need to go back, you can go back. If you wanted to re-watch it later, once again, these are posted on the Weebly course website. These ones specifically are going to be in a new section that I added. It's another page, and it says like physical science Schmidt out or something like that, so that you guys know that it's when I was out. Alright, so first of all, for solids, we know that solids, I should get rid of the pen. And let's get rid of that little dot. Cool. Okay, so first of all, we know that solids are substances where the particles are closely packed together. We're going to see them, the particles themselves are going to be really tiny, and as we see them, they are going to be right next to each other. So if I was to draw kind of like visually what this would look like, then I would see all these tiny atoms, and the tiny atoms are basically touching each other, and there's no room, no play in between them, and so this would be more of a crystalline solid the way I'm drawing it here, because I see that the substances are, you know, organized in a nice, neat pattern, and I can see then that they would have a rigid structure as opposed to an amorphous solid, which is going to be slightly different, and it's not going to be amorphous. Alright, number 2. There is an attractive force holding the molecules together, and we're going to talk about this attractive force when we get into chapter 12. So it's like a ways away. It's going to feel like eons by the time we get there. But this attractive force in between the particles themselves, it's called the strong nuclear force or a weak nuclear force. Strong nuclear force usually acts inside the nucleus of each atom to kind of hold everything together. The weak nuclear force acts to hold all the particles together themselves. So this attractive force that could be holding some solids together might be based off of the electrons, or it might be one of these nuclear forces. Do you really have to know what they are right now? No, just know that the particles are attracted to each other and they're held together tightly. And so in order to get rid of them, you'd have to add some energy to it. Okay, so the particles themselves, number 3, are also vibrating. So by vibrating, what I mean is if you were to be able to look at, say, your desk in front of you, and your desk, it looks like a solid, and it feels like a solid, and it looks like the particles aren't moving, but if you were able to look at a microscopic level, say like at the atom level, what you would see is the particles themselves would just be vibrating in place. And so there would be more or less a movement, kind of like, let me see if I can create something like that for you guys. Okay, so let's say this was an atom. Ultimately what's happening is it is just ultimately, let's see, it's just going to be sitting there, and it's not going to work. Oh, it wanted to copy it. So it's just basically moving in place and vibrating back and forth over and over again. And so you wouldn't be able to see these vibrations because it's more or less happening on a microscopic level. But instead, what's happening is they are going to be vibrating, and that vibration actually causes this attractive force a little bit as well, because by vibrating, they're moving the electrons around a little bit. All right, number 4. Naturally, like I was saying, they vibrate in place, so they do vibrate, but they stay in place. And lastly, this is the one that most of you have heard of before, solids have a definite shape and volume. So when we're looking at this definite shape and volume, this is the definition you would have learned, say, in like, I don't know, elementary school, middle school, something like that. Okay, so they're close, tightly packed together, attractive force acting between them, the particles are always vibrating, and they vibrate in place, and they have this definite shape and volume. Alright, so let's move on to liquids then. When we're looking at liquids, we're going to see something really similar to solids because the gap between the particles is still pretty small. So in number 1 here, the particles are still in contact with each other. However, what's going to happen is the particles are going to be in contact with each other in such a way, but they're going to be able to kind of like move past each other. So if you were to take your hands and you were to kind of like move them around like you were washing your hands, what would happen is as you're moving your hands over top of one another, they are kind of sliding past one another, but your hands are still in contact with each other. And that's the way the atoms are for liquids. So they're still in contact with one another. Okay. Number 2, there is an attractive force holding these molecules together. Once again, since they are so tightly packed together and close to one another, then they're going to be pulled towards one another. It's like a gravitational pull towards one another. Okay. Unlike solids, where the solids are rigidly defined and they just vibrate in place, number 3 here says the particles do slip past each other, like I was mentioning, and it's like, you know, washing your hands, where those particles are going to slip and slide past each other. They're going to be able to move around so that the particles can rearrange themselves and take the shape of the container, which is what you guys are normally used to when talking about liquids. Number 4, liquids have a definite volume but take the shape of their container. I will caution you that it's not the shape of a three-dimensional container in the sense of three-dimensional, but going in all directions. So it's going to be affected by gravity. These particles are going to be larger in size, and so therefore gravity is going to pull down on them because they have mass. And in doing so, what's going to happen is the particles are going to be able to take a three-dimensional shape of the container, like if you were to pour a glass of water, but the water is not going to magically just rise to the surface of the cup and then take like all the space up at the top of the cup as well. The only reason that would happen is maybe if you increase the temperature of the fluid, and then it might rise a little bit. Alright, lastly, number 5, liquid particles have more kinetic energy than solids. So we're kind of moving up the trend of kinetic energy. So solids had a small amount of kinetic energy. The particles were vibrating in place, so therefore they did have some kinetic energy. The particles are moving. But when we're looking at liquids, they're going to have more. They're able to move around a little bit more, so the particles are moving faster. So think like as the particles move around more or get faster, that means they have more kinetic energy. Alright, so I'm going to go through these pretty quick just because, I mean, most of you have learned about solids, liquids, and gases before. So solids and liquids, and naturally we're going to get to gases next. And so as we look at gases, what we're going to say is that gases themselves are going to be very similar to solids and liquids in the sense of how their particles move, because, I mean, depending on the substance, you're only going to have probably up to about 5,000 degrees separating their solid, liquid, and gas like states of matter. Okay, so number one, when looking at gases, gases say particles are not in contact with each other, and I mean this isn't like news to you. It's not a surprise. As you look at a gas, the particles are going to be moving around throughout the air. You're not going to see multiple particles next to each other, but instead there's going to be large gaps of space between them, and in doing so that enables them to travel to expansive spaces. So if I was to pump like small tiny blue particles into the corner of the room and you were able to kind of then visually see these particles, what would happen if they're in a gaseous state is they would eventually start to kind of distribute themselves around the room. It might not be evenly because there might be like air vents moving around and everything, but over time, if there was, say, no extra airflow, then they should, for the most part, evenly space themselves around the container or around the walls. Now you might see them kind of like hovering lower to the ground because, I mean, these are particles, they do have mass, so gravity would act on it, but I mean, it just kind of depends on the weight of the particles or the mass of the particles themselves. If it's a pretty light particle like hydrogen, then you're going to see a lot more of those particles being able to stay a little bit higher up in the air, especially because they have lower density. All right, number two, gases have enough energy to overcome these attractive forces, and that's evident in the sense that the particles are not in contact with each other anymore. So they gained enough energy that they started to move away. So it's like give a kid sugar, and the kid's going to want to run away from mom and dad and try and, break through and just run. And so in doing so, by giving them a little extra energy, they're able to kind of move around. Number three, particles move randomly in a straight line. So if I'm looking at these particles, the gaseous particles aren't going to move in a straight line until they come in contact with, say, another particle or the walls of the container that they are in. So if I'm talking about the gaseous particles moving through the air, they're traveling at extremely high speeds. I'm not going to tell you what it is because you might be coming in contact with that in one of your labs, but they move in extremely high speeds. And so these particles, they're going to be moving so fast in a straight line, as soon as they hit a wall, they're just going to bounce off. Or if they hit another particle, they're going to bounce off and deflect in a different direction. There might be a transfer of kinetic energy between them, which means that like a slower moving gaseous particle might hit a fast moving gaseous particle, and then it's going to gain kinetic energy and it'll start moving a little bit faster. Okay, number four. Gaseous particles, like I said, keep moving until they hit another particle or side of the container. So I'll leave that on there so you guys can kind of jot that down. And number five is one that you guys have seen before. So gases have no definite shape or volume, whereas solids had a definite shape and a definite volume. Liquids had a definite volume but not a definite shape. So they share that with gases, whereas they share the volume with solids. All right, on to plasmas. So plasmas is going to be this new part or state of matter for some of you, but it's probably something that you have seen or heard of before. So once again, plasmas are going to have this high energy, and the reason why they have this high energy is because the gas becomes ionized. And what it means to be an ion is the particles themselves are going to gain a certain amount of energy, and in doing so it actually splits up the atom. So the nucleus kind of stays off to one side, and then it's going to lose some of the electrons from the outside of the atom. In doing so, it's going to make it so that it has a positive portion. So you're going to see something with a positive charge and something with a negative charge. So plasma is going to have these positive ions, which we'll learn about a little bit later. They're called cations. And then the negatively charged particles are called anions. And so these particles, whenever the gas gains so much energy, what's actually happening is it's going so fast that the electrons just get stripped off. They can't compete, or the amount of force necessary to kind of hold them in place is not great enough, and so then they are stripped from the outside. They're too far away from the atom itself, and so they kind of move away. Then you also have number 2, substance becomes plasma at very high temperatures. Like I was mentioning, as they gain this extra kinetic energy, they're going to be moving very fast. And temperature is actually a measure of the amount of kinetic energy in a substance. So therefore, if I was to look at this idea of having very high temperatures, then this high temperature is going to tell me that they have a very high amount of kinetic energy. Okay. All right, to the third thing that you're going to want to jot down. So with plasma, the speed of particles is so fast that as the particles collide, electrons are stripped, like I was mentioning. So as they are moving, they get this high kinetic energy. The electrons are going to become stripped. They might either collide and then connect in with the other atoms that they are coming in contact with, or they just might be freely left alone by themselves, and in doing so it's going to leave these negatively charged portions. And since you are kind of taking an atom and breaking it apart into negative parts, then you also have to have the positive part, which is part of the nucleus. All right, last thing here, plasma is the most common form of matter, and I'll talk about that in a second. And so plasma makes up like parts of the universe, so we're going to see this all in the universe, specifically the stars. And so the percentage here, plasma makes up about 99% of the matter that you would find in the universe. That includes Earth, that includes the stars, everything. So typically when you're looking out into space, you are looking at plasma. Now where we would see this on Earth would be in the form of lightning. Lightning is a form of plasma. Also neon, like neon lights, or the fluorescent tube lights that you would see, say, in school. As you look up inside those light fixtures are typically going to be fluorescent light bulbs. And so what happens is you put a high amount of energy on either side of the light bulb, and what it does is it enables that energy to travel from one side to the other, and as it does so, it kind of ionizes the gas that's inside the tubes, which is what causes it to light up. So it creates this electrical flow as it kind of goes through. Okay, so that's plasmas. Plasmas have positive and negatively charged particles. They make up 99% of the universe. Basically, it's the most common form of matter that you're going to see. They gain the positive and negatively charged parts because they move so quickly. They have a high amount of kinetic energy, so you're going to see them at extremely high temperatures. All right, so that brings us to our fifth state of matter, which is Bose-Einstein condensate. And so this is the one that most of you probably haven't seen, so I believe I actually might have 10 items listed for these. It's just going to kind of go through a flow for you so you'll have a good idea as to what Bose-Einstein condensate really is. I'll do my best to explain it. Your book only briefly mentions it but doesn't talk about it in depth. Alright, so first of all, this is probably one of the most important things that you want to write down or know. I'm not going to require you to memorize a whole bunch about it, but BEC is a matter that is super unexcited. So some days it's kind of like you guys in class, where there's not a lot of excitement. But the reason why it's considered unexcited, it's not in the sense of, like entertainment value, but it's in terms of how quickly the particles are moving. So unexcited means basically low amount of kinetic energy. And so if I'm looking at the low amount of kinetic energy, these are super cooled. So this is at or below 0 Kelvin. So we'll say at 0 Kelvin. Okay. And so that means that what we're looking at here is something that is going to be moving around very, very slowly. And so the substance becomes BEC at very low temperatures, 0 K, like I mentioned. And the speed of the particles is so slow that as the temperature decreases, the energy is going to be the same for all the atoms. So it's like they kind of move and congeal as one. And that's what I got here. So I'll leave you guys a little bit of time here, or you could just have the substitute pause the video, and that way you'd be able to get everything down for Bose-Einstein condensate. So these once again occur at temperatures near 0 Kelvin. The atoms begin to clump. And so as they clump together, they're going to create a superatom. We can say it more or less kind of like flows like a wave. So you're going to see like the particles just kind of like moving on through real slowly. in more of like a wave pattern. Okay, and so they just kind of move together as one unit. So it's kind of like you'd be viewing the ocean in a sense, but not exactly. And so naturally they all, since they're kind of acting as one atom, they all take up the same space and properties. So as we're looking at them, they are all going to be kind of acting as just one big piece of matter. All right, moving on to the other ones now. Hopefully you guys paused or went back a little bit. Okay, so like I said, I had about 5 more for Bose-Einstein condensate. So first one, never mind, I don't. It's all exactly the same. Okay, so like I was mentioning before about the energy, ultimately this energy, this type of energy, is the kinetic energy that you guys were kind of looking at before, so we can kind of add in that this was kinetic. And if you want to kind of create this chart across the span of your notebook, then you can kind of see that the arrow here goes from low to high kinetic energy. And so as I'm looking at that, I might want to say, all right, I'm starting down here with Bose-Einstein condensate. And once again, this is going to be about 0 Kelvin, which is going to be really cold. Then you get to solids, and so solids are going to gain some kinetic energy, and we know that, you know, solids, it's kind of like room temperature for us. But, you know, it's going to form a solid at a lot lower temperature than what you guys are used to. And there are some liquids that would also be at room temperature, but you can see that the kinetic energy is starting to get a little bit higher. Then it gets into gases, so you're going to see that the kinetic energy is large enough for these gases that they begin to escape. And then lastly, you reach plasmas, which is going to be extremely high temperatures, so this is going to be in the thousands up here, if not 10,000s. Okay, so you're going to see that plasmas are going to occur at extremely high temperatures, gases occurring at, it kind of varies with the substance that it is. I mean, some metals are going to have gases that occur at in the probably like 2,000-3,000 thousand range in terms of temperature, and so you can see that the kinetic energy has a direct correlation then with the temperature, so you can kind of think solids are usually a little bit colder than gases and so on. Okay, so that's your kind of chart, your hierarchy, so you can get an idea as to what it looks like for the kinetic energy. Okay, this is the kind of steps that you guys would be doing in class. So if I was looking at these, then I would say, all right, if I, let's see, pick on the first one here, it says definite volume but not shape. So if I'm looking at something with a definite volume, that means that the particles got to be tightly packed together, but it doesn't have a definite shape like solids would, so I'm going to place it over in the liquids section. All right, ethanol. Many of you probably haven't heard of ethanol. Some of you may have. Ethanol is an additive that is placed into the gasoline that you would pump into your car, so that's typically in a liquid form. Same thing with water, although I could put solid, liquid, or gas for water, except for the fact that I have water vapor and iced over here. So water vapor is going to go over into gas, and we'll check these at the end. Ice, I think you guys know, is a solid. If it has a definite shape and volume, that's going to be in solid. Carbon dioxide is an example of a gas. Most kinetic energy out of these three, which one would be the most kinetic energy? It would be gas. If plasma was up here, we would add it there. Same shape as container. Now that could be a couple of these. Would it be solids? Nope. Could be liquids, could be also gases too. I'm just going to put in the liquid. Technically we know gases, it could also take the shape of that container. This has no shape or volume, so that's going to be a gas. Crystallized carbon. So like I was talking about before, there's something called crystalline or an amorphous structure. Crystalline would be like table salt, where it's going to be real rigid. It's actually going to be cubic in shape. And amorphous would be something along the lines of, say, like some lava form that kind of hardens really quickly, and so then the structure of it is not exactly any shape that you're normally used to. Alright, and least kinetic energy out of these, I would throw it into the solid section, so we'll see if we're correct. We'll check and see, and they're all good. Alright. So let's check it out again. Definite shape, going to be a solid. Looking at gold, that's going to be a solid. Coffee. Depends if you're talking about the grounds, but I'm guessing you're not. Carbon monoxide. Carbon monoxide is what you're usually testing for in your houses, and that comes in a gaseous form. You also want to be careful about, having a car running in an enclosed garage or something like that. That can also be a lot of carbon monoxide. Let's see, vibrate slowly. Well, the only one that vibrates would be solids. They vibrate in place. A table is considered a solid. An ice cube is a solid. Wood is a solid. Carbon is solid. That's what diamonds or coal are made out of. Flows freely. It could actually be a liquid or a gas. I'm going to go with a liquid. Typically when we talk about flowing, it's usually liquids, but both of these are fluids, so we could consider them both to be flowing freely. Vibrate fast. I'm guessing by vibrating fast, they're meaning traveling fast. It's the nice part about borrowing these kind of things from other people. All right, and sugar is going to be a solid. Looks like they got a lot of solids here. Indefinite volume. Something with an indefinite volume would have to be a gas because it has an indefinite shape as well. Oxygen is considered a gas, and I would say the dew is condensated water. So we'll check and see what we got here. And they're all good. All right. Okay, so there's a couple quizzes on here. We'll see. I'll give you guys a chance. I believe I had 2 quizzes on here. Yep, okay. So, molecules that move quickly, would you say it's a liquid, a solid, a gas, or condensation? Okay, if the molecules move quickly, I would say that it is a gas, that the molecules are moving quickly. Nice. Question 2, gas transforms to a liquid. We didn't talk about these ones yet. We're going to talk about these ones in the 3rd lesson, but gas transforming to a liquid, that would be what happens at night and why you have water on the grass, which would be condensation. Melting point for ice, we talked about this last chapter. I guess these are all, we'll consider them to be in Celsius. So melting point for ice, meaning that that is also the same thing as the freezing point, which should be 0 degrees. Liquid transforming to a gas, this is one that we will also see a little bit later. Measure of kinetic energy, I mentioned that kinetic energy has a direct correlation to which of these 4? Heat, temperature, melting, and cold. It's going to be temperature. Definite shape. The only one that has a definite shape is a solid. Matter that is moving has what kind of energy? Kinetic, good. The smallest building block of all matter? An atom. Ooh, that's spelled wrong. Indefinite volume. Indefinite volume. Indefinite volume, so that means that the volume is going to change. That would be a gas. And lastly, let's see, when a pot of water is heated, its kinetic energy is going to do what? So as I increase the temperature, what's going to happen to the kinetic energy? It depends with this question. If it is during the pot of water being heated, I would say that kinetic energy is going to increase though. All right. So I'll leave you guys with that. There's one more here, but we'll kind of leave it at that for now. So at this point, you should have a good idea as to what the 5 states of matter are, and just make sure you go through the checklist and see if there are any assignments that you want to try. And good luck and get on to the 2nd section.